the Kramers-Kronig relations. It turns out, if you're an electromagnetics person, it may surprise you that the Kramers-Kronig relations actually have nothing to do with electromagnetics. They come from linear system theory. But we realize that when we look at atomic scale resonances, this is a linear system, and we can apply the Kramers-Kronig relations to electromagnetics in that way. But it actually originated in linear systems. So that's where we'll start. We'll then derive the Kramers-Kronig relations. Then we'll write them for electromagnetics, and then we'll finish by discussing really why they're important in electromagnetics. Linear systems. This is definitely not going to be a comprehensive discussion of linear systems, but roughly we can say that if a system is linear, that we can characterize it with an impulse response. And we write that here as h of t. So if we have an input f and an output g, we can calculate the output by convolving the input with the impulse response. And then here's our integral equation to calculate that convolution. This is all a time domain thing. If we're interested in looking at this in the frequency domain, our impulse response is called a transfer function. And we have the Fourier transform of our input, we have the Fourier transform of our impulse response, and the Fourier transform of our output. And now it becomes very simple. It's just straightforward multiplication of our transfer function and our input to get our output. Let's think about what happens when we have a real function. And in this case, I'm calling that real function u of t. If that is purely real, and I calculate the Fourier transform, that Fourier transform is in general a complex number. It has a real and imaginary part. And the single prime indicates the real part, and the double prime indicates the imaginary part. Well, it turns out if that original function is purely real, then the real and imaginary parts of the Fourier transform actually have a symmetry. The real part is an even function. That means if we try to evaluate the even part at a negative frequency, that's the same as evaluating the real part at a positive frequency. The imaginary part of our Fourier transform is an odd function. So if we try to evaluate the imaginary part at a negative frequency, that's the same as evaluating the imaginary part at a positive frequency, but then made negative. Now, if this function is an impulse response, that implies that our transfer function has these same symmetry properties. That means the real part will have even symmetry and the imaginary part will have odd symmetry. And I'm summarizing those symmetry conditions here. And we will use those later when we derive the Kramers-Kronig relations. A real physical system cannot respond to an input before that input has happened. And this is called causality. So a causal system cannot respond to an input before that input has happened. And so imagine if you're driving your car, imagine the car horn would honk before you even press the horn. So that would not be good. It would require that your car read your mind, which really isn't possible. So we expect real physical systems to be causal. So if we look at the impulse response of a causal system, and if that input happens at time 0, then our impulse response has to be 0 for time values less than or equal to 0, and our output will also be 0 for time values less than or equal to 0. If we look at this in the frequency domain, and our transfer function, which we're writing as a capital H as a function of omega, here we're Fourier transforming our impulse response, but what we've done is we've multiplied that the impulse response by a step function. This is called the Heaviside step function, and it is 0 for all time values less than or equal to 0, and it is 1 for all time values greater than or equal to 0. And writing it this way will allow us to derive the Kramers-Kronig relations. Let's go ahead and derive the Kramers-Kronig relations. The first step in our derivation is to apply the convolution property. And what this says is if we are interested in the Fourier transform of the product of two functions, that is the convolution of the Fourier transform of those functions separately. So our overall transfer function is the Fourier transform of our impulse response. And we're writing that now as an ordinary impulse response times this Heaviside step function. So over on the right, we'll write this as the convolution of the Fourier transform of our impulse response convolve with the Fourier transform of our Heaviside step function. So we'll go ahead now and just plug in the expression for the Fourier transform of the Heaviside step function. And here we have the delta function. And the property of the delta function is that it's zero everywhere except at time zero. And the integral from minus infinity to positive infinity of that delta function is 1. So the area under this infinitely thin thing is 1. So that is the Fourier transform of our step function. And what we'll do here is we will just apply this convolution to both terms inside the square bracket. So we've expanded the equation, if you will. We're leaving this factor of 1 over 2 pi because we have a factor of square root of 2 pi here, another factor of square root of 2 pi, and that just ends up being 2 pi. The second step in our derivation is actually perform the convolutions, and we're just going to apply the integral we wrote a few slides ago. And so our first convolution will be written as this first integral from minus infinity to positive infinity, and this second convolution will be written this way. So if we perform the math, and essentially h or any function convolve with the delta function, it's just that function. In this case, we're also scaled by pi, so that's what we get here. We haven't done much to the second integral other than bring h to the numerator, and we'll leave it in this form for right now. Our next step is essentially solve this for h of omega. We see two occurrences here and here, and we want to collect all of those onto the left. So I expanded the equation, multiplied everything by 2 pi, and we see that these pi's have canceled here, just leaving a factor of 1/2, and the 1 over 2 pi goes over and pre-multiplies our integral. Now we have an h omega here, we have a 1/2 h omega here, so we can simply subtract a 1/2 omega from both sides, 1/2 h of omega from both sides, and then we cancel that factor of 2, and we end up with this final equation. We have an integral from minus infinity to positive infinity. We would like to eliminate the negative frequencies. And we have all these wonderful symmetry properties we can use to do that. So the first thing we'll do is separate this into two integrals. So we're integrating from negative infinity to positive infinity. So we can write this as an integral from minus infinity to 0, and then a second one from 0 to infinity. So this integral, no problems with. This is the integral that we have to play with. First thing I'll do is swap the limits here. When we swap the limits, we have to put a negative sign. At this point, I'm going to swap the sign of the limits. So we swap the sign of 0, it's still 0. We swap the sign up here, we go from minus infinity to positive infinity. And then what we have to do is swap the sign everywhere there's an omega. So there's a capital omega. So there's actually 3 occurrences over here. We swap the sign of all of them. And then I won't show it, but of course the last thing is this negative sign will cancel with this negative sign, and we end up with overall a positive integral. So we can take that positive integral here, and that we're replacing this first integral at the top. So now we have 2 integrals, and of course you can probably imagine on the next slide we're going to be combining those, because now they have the same limits on the integral, so we can combine them. This is where we were on the previous slide, and the whole thing here, we're going to do some math here. We're going to relate real and imaginary parts. So if we Fourier transform a real function, remember these symmetry properties. Well, it turns out we can summarize all that in one simple statement. If we try to evaluate a complex function at a negative frequency, that is the function evaluated at a positive frequency, but the complex conjugate. And that actually accounts for the symmetry for both the real and imaginary parts. Kind of neat way to write that. So we're going to combine these integrals. Then we're also going to apply the symmetry condition. And that's where we have this. We have h at minus omega. So we're going to write that now as a positive omega, but with a complex conjugate. Now we have 2 terms here with 2 different denominators, and we would like to combine these. So what we'll have to do is we're going to have to multiply this first term by little omega minus big omega divided by little omega minus big omega. So we're going to take this expression and write that as a ratio. We're going to take this expression, write that as a ratio that equals 1. We're going to multiply it out. We're going to combine everything. And after all that algebra, we end up here. So that's where we were on the previous slide. So we're going to do the math and just expand the numerator. So I'm going to take this h of big omega and multiply it by both of these, this h star of omega, and bring it in here and multiply it by little omega and big omega. Then I'm going to collect all of these terms, collect all the h's that are multiplying little omega, and then collect all the h's that are multiplying big omega. And this is where I end up. Now let's give some thought about this. We have the complex function plus its complex conjugate. Well, it turns out when you do that, you get 2 times the real part of that. The imaginary part vanishes because this complex conjugate essentially changed the sign, and then when you added it, it has vanished. Now over here, we have the complex function minus its complex conjugate. When we do that, it turns out we get twice the imaginary part. So that helps us simplify this. And we can write it this way now. And so we have an integral going from minus to infinity of the imaginary part, and another integral 0 to infinity of the real part. So that's where we were on the previous slide. Another thing I did on the left, instead of just writing as a single h, I've separated explicitly into its real and an imaginary parts. And if we look on the right, we can see that this will end up being purely real. And over here, this term, other than the j, but what's over here is also all purely real. And so multiplied by j, we'll get an imaginary number, but the thing multiplying the j is itself purely real. Now we can set the real and imaginary parts on both sides equal. So if we set the real parts equal, we get a first equation. And we set the imaginary parts equal, we get a second equation. And in fact, this really is the Kramers-Kronig relation for linear systems. So that's where we ended up. We had a transfer function that was in general complex, but it was the Fourier transform of a purely real and causal impulse response. And so it turns out because of all that, the real and an imaginary parts are related. And that's what the Kramers-Kronig relations are really telling us. And there's some useful parts of this. For example, maybe it's easy to measure the real part, but for whatever reason, not really feasible to measure the imaginary part. Well, this gives us a way to calculate the imaginary part from the real part. And that's very useful, particularly when we start talking about electromagnetics, because a lot of times certain things are easy to measure and not. The other thing this tells us is that we don't have as much freedom as we think here. We don't actually have 2 numbers over here. Yeah, we have 2 numbers, but one completely depends on the other. So we're not free to choose those functions completely separately and independently. We're limited in what we can do. And if we know one, we can calculate the other. Let's apply what we've learned about the Kramers-Kronig relations to electromagnetic systems. So maybe here's sort of the big aha. It turns out the electric susceptibility really is the impulse response of an atom. Therefore, it's a real physical thing. It must be causal. And we also know that it's purely real. We can Fourier transform that and also think about the susceptibility as a transfer function in the frequency domain. So given that we now know that our susceptibility is an impulse response, with the little epsilon naught being a little scaling factor there, we can take what we derived for the general transfer function and just write it for the susceptibility. So that is the Kramers-Kronig relations for the electric susceptibility. Let's move on. Well, we know that the susceptibility and permittivity are almost the same thing. If we add 1 to the susceptibility, that gives us permittivity. So in fact, we can write the Kramers-Kronig relation for the complex permittivity that relates the real and imaginary parts of that. We want to write the Kramers-Kronig relation that's relating the real and imaginary parts of refractive index, but the math gets a little weird, but there's an exception that makes this easier. And this is the idea of having a dilute media, which really means that the susceptibility is weak. So let's remember how refractive index and susceptibility are related. So refractive index is the square root of the relative permittivity, which is 1 plus the electric susceptibility. Now, if we have a dilute media, and this susceptibility is rather small, and in fact, if it's less than 1, we can use the binomial approximation to get rid of the square root. And instead of having the square root of 1 plus the susceptibility, it's 1 plus 1/2 the susceptibility. And of course, we can write this in terms of the real and imaginary parts of susceptibility with this requirement to use the binomial approximation. So we're limited here in what the susceptibility can be. Thus, we're calling this dilute media. So if we set the real and imaginary parts equal in this first equation, we can see that the ordinary refractive index is 1 plus 1/2 the real part of the electric susceptibility, and our extinction coefficient is 1/2 of the imaginary part of the electric susceptibility. So we can use those relations, go back to our Kramers-Kronig relation for susceptibility, and now write it again for our ordinary refractive index and extinction coefficient. So that's what we're doing here, the Kramers-Kronig relation for the complex refractive index. And we end up here. This is relating the real and imaginary parts of refractive index with the condition that this is only valid for dilute media. Now, it's more common when we're talking about refractive index actually to relate the ordinary refractive index to the absorption coefficient. So I'm not talking about the attenuation coefficient, we're talking about the absorption coefficient. So it's a slightly different relation. There's a factor of 2 hanging out here. So our absorption coefficient is 2 times K naught times the extinction coefficient. But we can take the equations from our previous Kramers-Kronig relation and now relate the refractive index to our absorption coefficient. So we have Kramers-Kronig relation that relates those. And this is actually probably the most common one you'll see. If you Google Kramers-Kronig relation for optics, that's the one you'll see. This is a neat one too. We can write a Kramers-Kronig relation that relates reflectance and phase. And this does something really neat for us, but let's just get into this. So our reflection coefficient, this is the one that's relating field amplitudes, not power. We write as a reflectivity times an e to the j, and this is the phase of a wave after reflection. And we can take the natural log of this equation and write it as the sum of a real and imaginary part. Well, that lets us write a Kramers-Kronig relation relating those two. After some math, getting rid of the minus infinity to positive infinity, making it 0 to infinity, we can write just the phase part of the Kramers-Kronig relation this way. And the reason I'm only writing one is generally this is how it's used. And this is really cool because measuring reflectance or just the reflectivity and not phase is very easy. It's very difficult to measure phase, but it is really easy to measure intensity. And so this Kramers-Kronig relation gives us a way just from intensity measurements to calculate what the phase was on reflection. I think that's pretty neat. So in conclusion, here is the meaning and the utility of the Kramers-Kronig relations in electromagnetics. And I have 3 main points. So the first one is it's very easy to measure loss through a sample. And so that'd be our absorption coefficient here, for example. Much more difficult to measure refractive index. But we can take a simple measurement, apply our Kramers-Kronig relation, and retrieve refractive index from it. Second point, we can take, again, an easy intensity measurement. In this case, it's reflectance. That's just a power measurement. And calculate what the phase was of reflection. And the third point, we're somewhat limited in material properties. We can't arbitrarily choose the real and imaginary part, and that's because they depend on each other. Appendix. I'd like to talk about a couple of things that I guess aren't really that important for understanding the Kramers-Kronig relations, but they're common questions, and things we need to know if we're actually going to use these to calculate things. The first is, let's look at this from the perspective of we've measured an absorption spectrum of something and we would like to calculate refractive index from that absorption spectrum alpha. Well, if we stare at this integral long enough, what we'll see is that there's a problem in the denominator. At some point, this big omega will equal little omega, causing the denominator to go to 0, causing the entire integrand to go to infinity. So what on earth do we do about this certain case? Well, there's something called the Cauchy principal value. What if we take this problem integral and we separate it into two different integrals? We know that the problem happens when big omega equals little omega. We have to integrate from 0 to infinity. So let's separate our single integral into two integrals. The first one will go from 0 up to omega, but minus some delta omega. So we're coming down below where we have this pole or this explosion to infinity by some delta omega. And then up here, we start at omega plus delta omega. So to the right of where that explosion happens, and then we finish integrating up to infinity. So we've sort of skipped over where we have this explosion, where this goes to infinity. Well, in the limit, as this delta omega goes to 0, this becomes exact. So in practice, we can actually let omega be something very small, and we can estimate this little missing gap in the middle of the integral just using the edge values of this little gap that we've skipped. Looking at this equation long enough again, there's another problem. We have to integrate all the way up to infinity. How on earth do we do that? Does that mean we have to take measurements all the way up to infinity? Well, I apologize for my hand sketch here, but what I've drawn is a typical absorption spectra as a function of frequency. And what we can see is it does a bunch of stuff, but usually there's a lower and an upper frequency, and below the lower frequency, it's 0. And above this upper frequency, it's 0. So anything we integrate above that upper frequency or below the lower frequency is just 0 anyway. And so we can skip it in our integral. So in fact, our integral from 0 to infinity really just ends up being an integral from omega 1 to omega 2, which is usually the spectrum over which we're making this measurement of absorption.